Hello, it's time once again to talk about the basics of vectors. We're on the third goal in this section, and that third goal is this. You're going to be able to determine whether pairs of vectors are equal, negative, or parallel vectors. Very straightforward. And most of these concepts are exactly what you would expect them to be. Let's go ahead and take a look. Let's get right into this right here. I've got several vectors drawn on the screen right here. You see vectors A through E. And we're going to group them into vectors that are equal, vectors that are negative, vectors that are parallel. And while doing so, of course, we'll talk about what the definitions for each of those things are. Now, without me having to say much, I think I could ask you to pick out a pair of vectors that are equal to one another, and you'd be able to do that pretty well, right? Vectors C and E would be the equal ones, wouldn't they? And of course, what is it that makes them equal? Well, they have the exact same size and direction, which is evidenced simply by writing their column vector forms or their unit vector forms right next to one another. In this case, the column vector form for each vector would be 3, 2. Very straightforward. All right, let's see if you can pick out a pair of vectors that you would think are negative vectors. Keep in mind that negative vectors have to be different than equal vectors in some way. I'm hoping that you chose vectors B and D, because although they are the same size, they go in exactly the opposite directions, and that's what negative vectors do, is they go in exactly the opposite directions. But they have the same size. Now let's suppose you didn't see these vectors, but you were given their component form in either column vector or unit vector form. The way you would recognize that they were negative vectors of one another is that the components of one would be exactly the opposite of the components of the other, which I'll write this way. Notice that for vector B you go right 1 and down 4, so this is its column vector form. And for vector D, you go left 1 and up 4, so that's its column vector form. Now I want you to pay attention to this little thing in front. I said basically that B equals the opposite of D. This negative sign right there is what's called a scalar. Not because it's a negative sign, but because we're taking the components of a vector and we're multiplying them by a scale factor, basically. Now we talked about how a vector is a quantity that has direction and it has size. Well, a scalar is also a quantity, but it only has size. It doesn't have direction. That's for another discussion. But nevertheless, if I multiply both of these components by this scalar, it equals this one. So they're opposites of one another, and that makes these two vectors negative vectors with one another. All right, now parallel vectors. This doesn't necessarily mean exactly what it does in geometry, although it's pretty close. One of the things we have to consider is that you can have vectors that are going one direction or another direction that can still be parallel to one another. Basically, the idea of parallel vectors is they have to be going the same or opposite directions. And size doesn't matter with whether vectors are parallel. Now, I said this doesn't work exactly like it does with in geometry, right? For instance, none of these vectors up here actually intersect one another, do they? Because they all end at their terminal points that you see. So we can't just define parallel as they don't intersect. In fact, you can have parallel vectors that do intersect one another. It's do they go the same direction or opposite directions? Let me give you an example of where they do intersect one another, by the way. You see that vector F that I drew, it runs right into vector D. They share a point, in fact, but they're still parallel because they're going exactly the same direction. All right, so how do you determine they're going the same or opposite directions? Well, it has to do with that scalar idea again. Have you noticed any vectors that are parallel to one another? Well, let's start with, say, A and C. Let's not go through every pair, but let's pick a couple pairs. A and C would be a pair that works. Now, you've got to be able to determine this using either the column vector form or the unit vector form, right? So let me write the column vector form for those two vectors. And I think you'll agree with this equation that I wrote here. If you were to take the column form for vector C and multiply both of its components by -2, you would get -6, -4. And so here's a definition you can use to determine if two vectors are parallel. If you can write one vector as a scalar of another vector, all right, this one is twice -2 times this one, that means that they're parallel to one another. And it doesn't matter what this scalar is, as long as that scalar times this vector would equal the other vector. That makes them parallel. All right, now some other pairs of parallel vectors. It would be redundant to say that C is equal to E, because if they're equal, they're going to have to be parallel as well, because they're already going in the same direction. It would be redundant to say negative vectors are parallel, because they go opposite directions, so they already fit that category. So we don't need to say B is parallel to D, but we could say F is parallel to D. And the reason we can say it is because we can write the component form of F as the component form of D times the scale factor, that scale factor happening to be 1/2, right? 1/2 times -1 equals -1/2. 1/2 times 4 equals 2. Those vectors are parallel. And it's this idea of scalars that you're going to use to determine if two vectors are parallel, and you're going to do that right now. I want you to figure out which of these vectors are parallel to the vector -3, 5. So take some time and do that real quick, please. Turns out 3 out of 4 of them are. Let me highlight those for you and show you how each could be written as a scalar, as this times a scalar. For the first one, the scale factor would be -1. For the second vector, the scalar would be -3, right? For the last one, the scale factor would be 1.5. You can double check the math on that if you didn't get that before. Part C wasn't switching the horizontal and vertical components doesn't make two things parallel to one another. It doesn't make them opposite directions or anything. You're not going to find any number that you can multiply 5 by that gives you -3, that you can also multiply -3 by that would give you a 5. Just impossible. All right, so those are your parallel vectors. I want to do one more problem with parallel vectors here, and this is a 3-dimensional one. I want you to find the values of A and B that would make these two vectors parallel. Keep in mind, one would have to be a scalar of another. Now, I want you to notice what I'm doing here. In order to make the scalar, we had to compare one pair of components that we already knew the scale factor for. If you multiply this 2 times -3, it gives you a -6, right? There should be a -6 right there. So we're going to multiply each of these values by -3 in order to get the corresponding values over there, meaning that 4 times -3 will give me A, so A is going to be -12, and B times -3 would have to give me -2, right? This times -3 would have to give me that, which means that B is 2/3. All right, that's how you work with equal, negative, and parallel vectors. Thanks for watching. Let's keep hitting this chapter hard. See you next time.